limit will depend on the altitude. So let's say the altitude is increasing, so this is decreasing, and one limit is decreasing. And again, what do you see? The pilot or the fuel control system of the engine is replacing this limit, thermal limit, and this limit, mechanical limit, for whatever the value of the flat rating temperature by one single limit and one limit that is changing following what I have explained here. Bit more complicated because here you have for the first time that the N1 limit is changing in function of two parameters when you are in the mechanical zone, in the mechanical limiting or limited zone. But very powerful. You were facing a critical problem that is the safety of the engine in a very complex situation where you have parameters that are the ones to consider, but that are not measurable, and you replace that by very simple laws that I will show you with values in the slides that I will comment and that I will put on the UV or on Toledo, and you replace two unmeasurable parameters by one single, very easy to measure parameter with a very easy law in the case of the EPR, a bit more complicated in the case of the General Electric engine. Okay? So very powerful the use of the thrust setting parameter, and very powerful the application that we see here at the level of the flat rating. There is another example that I would like to show you. This is the cruise flight. So an engine, an aircraft, is cruising at a certain Mach number and at a certain altitude. So normally an aircraft, we can discuss about that is changing the altitude depending on the gross weight, but over a certain distance, the aircraft is flying constant altitude, constant Mach number. What are the equations governing the problem? The gross weight is equal to the lift, and the thrust is equal to the drag. And the lift is equal to 1/2 gamma PA multiplied by CL multiplied by the wing area square multiplied by MA square. And the drag, this is 1/2 gamma PA CD total, CD0 and CDI multiplied by by the wing area multiplied by Mach square. Okay? And the good question is, how is the pilot looking at the engine rating? So what is the pilot doing with the throttle? So is the pilot playing with the throttle to reach that? What is he doing exactly? And what is he doing also depending on conditions like when you are in the winter compared to the summer, because the outside air temperature is not the same. As I said, so he's flying at constant Mach number, because this is indicated by the aerodynamics of the aircraft. This is also a constant, the wing platform area. We are at a constant temperature, so PA is also constant. These are also constants, okay? And so, over a certain length of the flight, maybe it is 1 kilometer, maybe it's 10 kilometers, maybe 100 kilometers, depending on the change of the gross weight. Over a certain distance, the gross weight is equal to a constant, okay? And so you see that as the gross weight is constant, the lift is constant. And if the lift is constant, CL is constant in this equation. But if CL is constant, then the CD total is constant. And if the CD total is constant, the drag is constant. And this is also constant. So you say me, what have you proven? That the thrust is constant. It's not the thrust that is constant. This is what we call, you have had some classes with Colonel Recker or with other people, this is what we call the requested or indicated thrust that you have here. This is the thrust that you need. The thrust that you need is constant. And that means it is not changing in function, for example, of the outside air temperature. Okay? Or are you doing that? Or are you doing that? So, this is, again, something that you can take care about by using the thrust setting parameter. By using the thrust setting parameter and by using the reduced parameters. So the corrected or reduced parameters. So we see that the requested thrust is constant. And the requested thrust must be constant, and the requested thrust, if you express it in reduced parameters, this is the requested thrust divided by delta ambient, and you can indicate that this is a certain function of the Mach number and, for example, the EPR. Okay? And we see that this is constant, so we fly at constant Mach number, so this is also constant. We fly at constant altitude, so this is also constant. So how is the pilot governing a constant altitude flight at a constant Mach number? By choosing the EPR constant. So whatever the change you could have, for example, in the outside air temperature, the pilot will look at what? The EPR. And the EPR during a cruise flight with a constant value of the gross weight must be constant. Okay? Of course, when the gross weight will decrease, the lift will decrease, this 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 will decrease, and you will also decrease the EPR. And you can have a law that is indicating the value of the EPR in function of the gross weight that you can implement in a system governing the change of the EPR in function of the gross weight depending on the fuel flow, because the fuel flow is known. You have a measurement of the fuel flow, so you know what is the change of the gross weight, and if you have the relation between EPR and gross weight, you can change the gross weight, the EPR automatically in flight. Of course, if this is not the EPR that you are selecting here, but N1 divided by the square root of the total temperature, this is this parameter that is constant. You see? And this parameter is constant, so if you change the OAT, you see that you will change N1 proportionally with the square root of the change of the OAT. So you see that this methodology is extremely powerful, because you can regulate the engine automatically in order to fly at constant altitude, at constant speed, with a certain gross weight in function of the UAT just by taking this constant and changing N1 proportionally with the square root of the change of the UAT. And if you have the link between this parameter, including the rotational, the square root in function of gross weight, you can take a very easy control of the engine to stay at constant altitude, constant Mach, with a reduction of the gross weight by just adapting N1, depending on the change of the gross weight and the change of the outside air temperature. Or here, constant EPR decreasing with the gross weight. So very powerful, the, let's say, way to use these combined, you see, reduced variables or corrected variables and these famous thrust setting parameters which are here. Okay? And I would also like to introduce a final case that is extremely well known to show what you have to do or what you do not have to do. So we have seen very clearly, it is behind this board, that the thrust is proportional with the EPR. You could say the thrust is, you could write an equation like thrust is K multiplied by the EPR. Okay? The EPR, this is PT4 divided by PT1. Okay? And of course, there is a very dangerous situation. This would be a situation where you have ice formation, ice accretion, icing inside the intake. I'm discussing that because Thursday of next week, I will start discussing about the intakes. And we will see that at takeoff, there is a very clear danger of icing, ice formation, ice accretion inside the intake. And if you put a nice layer on the sensor, on the pitot tube, measuring PT1, PT1 is going down, is at the limit equal to 0. If you divide something by 0, it gives the impression that the EPR is very high. If the EPR is very high, you have the impression that the thrust is very high. You try to take off, you don't have enough thrust, and you fall into the river that is at the end of the runway. This has been the famous accident of the Potomac River in Washington State, in Virginia, years ago. And of course, if you have made such a mistake, first you are fired by the company, and also what do you need to do? You need to put anti-icing here. You need to put an heat-up system, a heater,